Functions. Functions are prevalent in Rust code. You've already seen one of the most important functions in the language, the main function, which is the entry point of many programs. You've also seen the fn keyword, which allows you to declare new functions. Rust code uses snake case as the conventional style for function and variable names, in which all letters and lowercase and underscore separate words. Here's a program that contains an example function definition. Another function. We define a function in Rust by entering fn followed by a function name and a set of parentheses. The curly brackets tell the compiler where the function body begins and ends. We define a function in Rust by entering fn followed by a function name, fn followed by the function name, and a set of parentheses. The curly brackets tell the compiler. The curly brackets tell the compiler where the function body begins and ends. We can call any function we've defined by entering its name followed by a set of parentheses. We can call any function we've defined by entering its name followed by a set of parentheses. Because another function is defined in the function program, it can be called from inside the main function. Note that we defined another function after the main function in the source code. We could have defined it before as well. So after the main function in the source code, we could have defined it before as well. Rust doesn't care where you define your functions, only that they are defined somewhere in the scope that can be seen by the coder. Let's start a new binary project named functions to explore functions further. Place the another function example in src main rs and run it. You should see the following output. Hello world, another function. The lines execute in the order in which they appear in the main function. The line execute in the order which they appear in the main function. First, the hello world means the hello world message prints. Hello world message prints, and then another function is called and its message is printed. Parameters. We can define functions to have parameters, which are special variables that are part of a function's signature. When a function has parameters, you can provide it with concrete values for those parameters. Technically, the concrete values are called arguments. But in casual conversation, people tend to use the words parameter and argument interchangeable for either the variables in a function's definition or the concrete values passed in when you call a function. In this version of another function, we add a parameter, file name src main.rs. Try running this program, you should get the following output. The declaration of another function has one parameter named x. The declaration of another function has one parameter named x. The type of x is specified as i32. When we pass 5 into another function, the println macro puts 5 where puts 5 where the pair of curly brackets containing x was in the format string. In function signatures, you must declare the type of each parameter. In function signature, you must declare the type of each parameter. What's clear? Okay. So this is a deliberate decision in Rust design, requiring type annotations in function definitions means the compiler almost never needs you to use them elsewhere in the code to figure out what type you mean. The compiler almost never needs you to use them elsewhere in the code. The compiler is also able to give more helpful error messages if it knows what type of the function expected. When defining multiple parameters, separate the parameter declarations and with commas like this. Okay. So the example creates a function named print to label the measurement with two parameters. The first parameter is named value. The first parameter is named value and ni32. And ni32. The second is named until label, and is type char. The function then prints text containing both value and the unit label. The function then prints text. This function then prints prints text containing both value and until label. Yep, unit label. So let's try running this code. Replace the program currently in your functions project's src main.rs file. With the preceding example and run it using cargo run. The measurement is 5 hours. Because wait a second, 5. Because we called the function with 5. Because we called the function 5 as the value for value. Because we called the function with 5. Because we called the function 5. Because we called the function with 5. Because we called the function with 5. Because we called the function with 5 as the value for value. Because we called the function with 5 as the value for value and h as the value for unit label. The program output contains those values. Question 1. The keyword for declaring a new function in Rust is fn. Question 2. Determine whether the program will pass the compiler. If it passes, say what will happen when it is executed. If it does not pass, say what kind of compiler error you will get. So let's see F0. So it doesn't compile, it does not compile because of line 1. Submit. Correct, because of the type. Statements and expressions. Function bodies are made statements and expressions. Okay. Function bodies are made up of a series of statements. Bodies are made of a series of statements, optionally ending in an expression. So far the functions we've covered haven't included an ending expression, but you have seen an expression as a part of a statement. Because Rust is an expression-based language, this is an important distinction to understand. Because Rust is an expression-based language, this is an important distinction to understand. Other languages don't have the same distinctions. So let's look at what statements and expressions are and how their differences affect the bodies of functions. Statements are instructions that perform some action and do not return a value. It does not return a value. Expressions evaluate to a resulting value. Let's look at some example. We will actually already use the statements and expressions, creating a variable and assigning a value to it with the let keyword. Let keyword is a statement. Listing 3-1 let y equals to 6 is a statement. A main function declaration containing one statement. Function definitions are also statements. The entire preceding example is a statement in itself. Statements do not return values. Statements do not return values. Those statements do not return values. Therefore, you can't assign a let statement to another variable. You cannot assign a let statement to another variable. Oh, this one. Because it does not return anything. As the following code tries to do, you will get an error. Oh, yes. When you run this program, the error you will get look like this. Expected expression found a statement. Variable declaration using let is a statement. Variable declaration using let is a statement. Let expression in this position is unstable. See blah 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 for more information. Unnecessary parentheses around the assigned value. Unnecessary parentheses. Remove these parentheses. For more information about this error, try Rostig explain blah blah blah. Okay. So the let y equals 6 statement does not return a value, so there isn't anything for x to bind to. This is different from what happens in other languages such as C and Ruby, where the assignment returns the value of the assignment. Those languages you can write x equals y equals 6. And have both x and y have the value 6. That is not the case in Rust. Expressions evaluate to a value and make up most of the rest of the code that you will write in Rust. Expressions evaluate to a value and make up most of the rest of the code you will write in Rust. Consider a math operation such as 5 plus 6, which is an expression that evaluates to the value 11. Consider a math operation. Consider a math operation. Consider a math operation. Consider a math operation. Consider a math operation such as 5 plus 6, which is an expression that evaluates the value 11. Consider a math operation. Consider a math operation such as 5 plus 6, which is an expression that evaluates the value 11. Expressions can be part of statements. In listing 3-1, the 6 in the statement let y equals 6 is an expression. 6 in the statement is an expression. Okay, that evaluates the value 6. Calling a function is an expression. Calling a function is an expression. Calling a macro is an expression. A new scope block, created with curly brackets is an expression. A new scope is this is a curly expression. For example, okay. So this is okay. So it's a block that in this case evaluates to 4. That value gets bound to y. That value, okay, yeah, y. As part of the let statement, note that the x plus 1 line doesn't have a semicolon at the end. Like most of the lines you've seen so far, expressions do not include ending semicolons. If you add a semicolon to the end of an expression, you turn it into a statement, and it will then not return a value. Keep this in mind as you explore function return values and expressions next. Functions with return values. Functions can return values to the code that call them. Functions can return values to the code that calls them. So can return values to the code that calls them. We don't name return values, but we must declare their type after an arrow in Rust. In Rust, the return value of the function is synonymous. The return value of the function is synonymous with the value of the final expression in the block of the body of a function. You can return early. You can return early from a function by using the return keyword and specifying a value, but most functions return the last expression implicitly. Here's an example of a function that returns a value. There are no function calls, macros, or even let statements in the 5 function. Just a number 5 by itself. That's perfect. That's a perfectly valid function in Rust. Note that the function's return type is specified too, i32. Try running this code. The output should look like this. The value of x is 5. The 5 is in the 5 number 5 in 5 function is the function's return value, which is why the return type is i32. Let's examine this in more detail. There are 2 important bits. First, the line let x equals 5 function call shows that we are using the return value of a function to initialize a variable. Because of function, 5 returns 5. 5 returns number 5. That line is the same as the following. Second, the 5 function has no parameters and defines the type of the return value, but the body of the function is only 5 with no semicolon, because it's an expression whose value we want to return. Let's look at another example. Plus 1, 5 here, 5. Okay. Running this code will print the value of x is 6, but if we place a semicolon at the end of the line containing x plus 1, changing it from an expression to a statement, we will get an error. Compiling this code produces an error. The main error message, mismatched types, reveals the core issues with this code. The definition of the function plus 1 says that it will return an i32. Implicitly returns blah 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 blah, as its body has no tail or return expression. The main error message, mismatched types, reveals the core issues with this code. The definition of the function plus 1 says that it will return an i32. The definition of the function definition of the function plus 1 says that it will return on I32. I32, okay. But same as don't evaluate a value, which is expressed by tuple, empty tuple, which is the unit type, yes. Therefore, nothing is returned, which contradicts the function definition and results in an error. In this output, Rust provides a message to possibly help rectify this issue. It suggests removing the semicolon, which would fix the error. In Rust, a curly brace block like is curly brace block is an expression. An expression and a synthetic scope. 1 and 3. Submit. Determine whether the program will pass the compiler. Determine whether the program will pass the compiler. If it was okay. So this program doesn't compile. Okay. fx so fxf and then I32 x plus 1. So here block this evaluates to 2. So it evaluates to 2 and then 2 goes out of here. Okay. Yep, this evaluates. 1 plus 1, 2, 2 plus 2 plus 1, 3. Yes. All programmers strive to make their code easy to understand, but sometimes extra explanation is warranted. All programmers strive to make their code easy to understand, but sometimes extra explanation is warranted. In these cases, programmers leave comments. In these cases, programmers leave comments in their source code that the compiler will ignore, but people reading the source code may find useful. Here's an example. Here's a simple comment. In Rust, the idiomatic in Rust, the idiomatic comment starts a comment with 2 slashes, and the comment continues until the second of the line. And the comment is continuous until the end of the line. For comments that extend beyond a single line, you will need include a double slash on each line like this. Yes. So comments can also be placed. Comments can also be placed at the end of the line containing code. But you will more often see them used in this format, with the comment on a separate line above the code it's annotating. But you will more often see them used in this format with the comment on a separate line above the code it's annotating. Rust also has another kind of comment, documentation comments, which we will discuss in the publishing a crate to crates.io section of chapter 4. Chapter 14. Rust also has another kind of comment. Documentation comments, which we will discuss in the publishing a crate to crates.io section, chapter 14. Rust is also another kind of comment. Okay, we will discuss in the okay. Control flow, the ability to run some code depending on if a condition is true. Control flow, the ability to run some code depending on if a condition is true. The ability to run some code. The ability to run some code depending on if a condition is true. Or run some code repeatedly while a condition is true. Or basic building blocks in most programming languages, the most common constructors that let you control the flow of execution of the Rust code are if expression and loops. The ability if condition is true, or run some code repeatedly while a condition is true, are basic building blocks in most programming languages. The most common constructors that let you control the flow of execution of Rust code are if expression and loops. If expressions. An if expression allows you to branch your code depending on conditions. You provide a condition and then state. If expressions, an if expression allows you to branch your code. An if expression allows you. An if expression here allows you to branch your code depending on conditions. You provide a condition and then state, if this command is met, run this block of code. If the condition is not met, do not run this block of code. Create a new project called branches. Create a new project called branches. Create a new project with called branches in your project directory to explore if expression. In the src main.rs, input the following. All if expressions start the keyword with the keyword if, followed by a condition. In this case, the condition checks whether or not the variable number has a value less than 5. We place the block of code to execute if the condition is true immediately after the condition inside the curly brackets. A block of code associated with the condition is in. We place the block of code to execute if the condition is true. We place the block of code. We place the block of code. We place the block of code to execute if the condition is true immediately. We place the block of code to execute if the condition is true immediately after the condition. Execute immediately after the condition inside the curly brackets. Blocks of code associated with the conditions in if expressions. Blocks of code associated with the conditions in if expressions are sometimes called arms. Just like the arms in match expressions that we discussed in the comparing the guess to the secret number section of chapter 2. Optionally, we can also include an else expression, which we choose to do here, to give the program an alternative block of code to execute should the condition evaluate to false. If you don't provide an else expression and the condition is false, the program will just skip the if block and move on to the next bit of code. Try running this code. You should see the following output. Optionally, we can also include an else expression which we chose to do here. To give the program an alternative block of code to execute should the condition evaluate false. An alternative block of code to execute should the condition evaluate. Should the condition evaluate the false. To give the program an alternative block of code to execute. What? Optionally, we can also include an else expression which we chose to do here. To give the program an alternative block of code to execute. Should the condition evaluate to value first. What? If you don't provide an else expression and the condition is false, the program will just skip the if block and move on to the next bit of code. Try running this code. You should see the following output. Condition was true. Well, let's see here. Yep. What the f does that mean? If you don't provide an else expression and the condition is false, the program will just skip the if block and move on to the next bit of the code. Try running this code. You should see the following output. Let's try changing the value of a number to a value what makes the condition false to see what happens. Run the program again and look at the output. Let's try changing the value of a number. Let's try changing the value of number to a value that makes the condition false to see what happens. Run the program again and look at the output. It's also worth noting that the condition in this code must be a bool. It's also worse nothing that the condition in this code must be a bool. If the condition isn't a bool, we will get an error. For example, try running the following code. Oh, the if condition evaluates the value of 3 this time and Rust throws an error. It's also worth noting that the condition in the code must be a bool. It's also worth noting that the condition in this code must be a bool. Worth noting shit. For example, we're running following code. Try if condition evaluates to a value of 3 this time and Rust throws an error. The error indicates that Rust expected a bool but got an integer. The error indicates that Rust expected a bool but not an integer, but got an integer. Okay, unlike a language such as Ruby and JavaScript, Rust will not automatically try to convert non-Boolean types to a Boolean. You must be explicit and always provide if with a Boolean as its condition. If we want the if code block to run only when a number is not equal to 0, for example, we can change the if expression to the following. Makes sense. Running this code will print the number was something other than 0. You can use multiple conditions by combining if and else is an else if expression, for example. You can use multiple conditions. You can use multiple conditions by combining if and else. You can use multiple conditions by combining if and else and in an else if same expression. Combining if and else in an else if expression. Combining if and else in else. Okay. This program has 4 possible passes it can take. After running it, you should see the following output. Number is divisible by 3. This program has 4 possible passes it can take. After running it, you should see the following output. Number is divisible by 3. When this program executes, it checks each if expression in turn and executes the first body for which the condition holds true. Note that even though 6 is divisible by 2, we don't see the output number is divisible by 2, nor do we see the number is not divisible by 4, 3, or 2 text form, the else block. When this program executes, it checks each if expression in turn and executes the first body for when this program executes. When this program executes, it checks when this program executes, it checks when this program executes, it checks each if expression in turn and executes the first body for which the condition is holds true. Note that even though 6 is divisible by 2, we don't see the output number is divisible by 2, nor do we see the number is not divisible by 4. 3 or 2 text from the else block. That's because Rust only executes a block for the first true condition, and once it finds this one, it doesn't even check the rest. Using too many else if expressions can clutter your code. So if you have more than one, you might wanna refactor your code. Chapter 6 describes a powerful Rust branching construct called match for these cases, using if in a let statement, because if is an expression. Using if in a let statement. Because if is an expression. We can use it on the right side of the let statement to assign the outcome to a variable, as in listing 3-2, assigning the result of an expression into a variable. Oh, like this. 5 is 5, okay, makes sense. The number variable will be bound to a value based on the outcome of the if expression. Run this code to see what happens. The number variable will be bound to a value based on the outcome, the if expression. The number variable will be bound to a value. The number variable will be bound to a value. The number variable will be bound to a value based on the outcome of the if expression. Run this code to see what happens. Running target debug. The value of number is 5. Remember that blocks of code evaluate to the last expression in them. Remember that blocks of code evaluate to the last expression in them. Remember that blocks of code evaluate to the last expression in them. And numbers by themselves also And numbers by themselves are also expressions. In this case, the value of the whole if expression depends on which block of code executes. This means that values that have the potential to be results from each arm of the if must be the same type. In listing 3-2, the results of both the if arm and the else arm were i32 integers. If the types are mismatched, as in the following example, we will get an error. In listing 32, the results of both the if arm and the else arm were i32. In listing 32, in listing 3-2. In listing 3-2. In listing 3-2. In listing 3-3, in listing 3-2 here. The results of both the if arm and the else. And in listing 3-2, the results of both the if arm. Results of both if arm and the else arm were i32 integer. If the types were mismatched, in the following example, it will get an error. When we try to compile this code, we will get an error. The if and else arms have value types that are incompatible, and Rust indicates exactly where to find the problem in the program. Expected integer found str. Expected because of this. The information about this error trials. Okay. The expression in the if block evaluates to an integer. The expression in the if block evaluates to an integer, and the expression in the else block evaluates a string. This won't compile. This what? The expression in the if block evaluates to an integer. The expression in the if block. The expression in the if block evaluates to an integer, and the expression in the else block evaluates to a string. This won't work because variables must have a single type. And Rust needs to know at compile time what type the number value is. Definitely, what? What? Knowing the type of number lets the compiler verify the type is. Knowing the type of number lets the compiler verify the type is valid elsewhere we use a number. Knowing the type of 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 number lets the compiler verify the type is valid everywhere we use number. Knowing the type of number lets the compiler verify the type is valid everywhere we use number. What? Knowing the type of number lets the compiler verify the type is valid everywhere we use a number. Rust wouldn't be able to do that if the type of number was only determined at runtime. The compiler would be more complex and would make fewer guarantees about the code if it had to keep track of multiple hypothetical types for any variable. The compiler would be more complex and would make fewer guarantees. True, false, these two pieces of code have the same effect on X. Let me X. True, false, these two pieces of code have the same effect on X. True, false, these two pieces of code have the same effect on X. True, false, these two pieces of code. True, false, these two pieces of code. True, false, these two pieces of code that have the same effect on X. Same effect on X. Okay. Conde 1, 2. If conde x equals 1, x equals 2. Same. True. Determine whether the program will pass the compiler. Determine whether the program will pass the compiler. Determine whether the program will pass the compiler. Okay. This program, let's see, true. Same ones. What is this? What the fuck is this? X is true. And this is a statement. Statements cannot be evaluated. Does not compile. Select 3. What? Shit. The error occurs on the line 3. I'm so confused. So shit. Repetition with loops. Repetition with loops. It's often useful to execute repetition with loops. It's often useful to execute the block of code more than once. For this task, Rust provides several loops, which will run through the code inside the loop body to the end, and then start immediately back at the beginning. To experiment with loops, let's make a new project. To experiment with loops, let's make a new project called loops. Rust has 3 kinds of loops: loop, while, and for. Let's try each one. Repeating code with loop. The loop keyword tells Rust loop, while, and for. Repeating code with loop. The loop keyword tells Rust to execute a block of code. The loop keyword tells Rust to execute a block of code over and over again forever until you explicitly tell it to stop. As an example, change the src file in your loops directory to look at like this. When we run this program, we will see again. When we run this program, we will see again printed over and over continuously until we stop the program manually. Most terminals support the keyboard shortcut Ctrl-C to interrupt the program that is stuck in a continual loop. Give it a try. Give it a try. When we run this program, we will see again printed over and over continuously until we stop the program manually. Most terminals support the keyboard shortcut key Ctrl-C to interrupt the program that is stuck in a continual loop. Give it a try. The symbol C represents where you press it. Ctrl-C. The symbol C represents where you press the Ctrl-C. The symbol C represents where you press. Okay, you may or may not see the word again printed after the C, depending on where the code was in the loop when it received the interrupt signal. Code was in the loop when it received the interrupt signal. Unfortunately, Rust also provides a way to break out of a loop using code. You can place the break keyword within the loop to tell the program when to stop executing the loop. Recall that we did this in the guessing game in the quitting after a correct guess section of chapter 2 to exit the program when the user won the game by guessing the correct number. We also use the continue in the guessing game, which in a loop tells the program to skip over any remaining code in this iteration of the loop and go to the next iteration. Returning values from loops. Returning values from loops. One of the uses of the loop. Returning values from loops. One of the uses of a loop is to re-entry an operation you know might fail, such as checking whether a thread has completed its job. You might also need to pass the result of that operation out of the loop to the rest of your code. One of the uses of a loop is to retry an operation you know might fail. Wait a second. Returning values from loops. Returning values from loops. Returning values from, okay. One of the uses of a loop is to retry an operation you know might fail, such as checking whether a thread has completed its job. You might also need to pass the result of that operation out of the loop to the rest of your code. You might also need to pass You might also need to pass the result of the operation out of the loop. You might also need to pass the result of the operation out of the loop to the rest of your code. You might also need to pass the result You might also need to pass the result. Also need to pass the result of the operation out of the loop. You might also need to pass the result of the operation out of the loop to the rest of your code. To do this, okay, you can add the value you want returned after the break expression you use to stop the loop. That value will be returned out of the loop, so you can use it as shown here. Before the loop, we declare a variable named counter and initialize it to 0. Then we declare a variable named result to all the value returned from the loop. On every iteration of the loop, we add 1 to the counter variable and then check whether the counter is equal to 10. When it is, we use the break keyword with the value counter times 2. After the loop, we use a semicolon to end the statement that assigns the value to result. Finally, we print the value in result, which in this case is 20. When it is, we use the break keyword with the value counter times 2. When it is, wait a second, we add 1 to the counter variable and then check whether the counter is equal to 10. When it is, we use the break keyword with the value counter times 2. After the loop, we use a semicolon. After the loop, after the loop, we use a semicolon to end the statement that assigns the value to result. After the loop, we use a semicolon. After the loop, we use a semicolon. We use a semicolon to end the statement that assigns the value to result. After the village is used the break keyword with the after the loop we use a semicolon to end the statement that assigns the value to result. Finally, we print the value in result, which in this case 20. Finally, we print the value result in the loop labels to disambiguate between multiple loops. If you have loops within loops, break and continue applied to the innermost loop. Loop labels is between multiple loops. What? Oh, loops. Loops. Labels. Loop labels. Loop labels to loop labels is between multiple. Okay. If you have loops within loops, break and continue applied to the innermost loop at that point. You can optionally specify a loop label on a loop that we can then use with the break or continue to specify that those keywords apply to the labeled loop instead of the innermost loop. Loop labels must begin with a single quote. Here's an example of with two nested loops. Continuing here and then loop here. Loop here continuing and break continuing. The outer loop has the label counting up, and it will count up from 0 to 2. Loop. So it goes inside here, and then when it becomes wait a second, 10, 9, break. When it's 2, okay. So print the remaining 0. Where is it? Count 0, remaining 10, and then not 9, so moves, and then counter 9, and then it becomes 0, 9, and then breaks, so it goes here, and then +1, and then it go here, and then push the 1, and then here, and then it's at the time 10 again, yes, 10 again, and then breaks, then 9 breaks, 1, okay, makes sense. So A program will often need to evaluate a condition within a loop. A program will often need to evaluate a condition with a loop. While the condition is true, the loop runs. When the condition ceases to be true, the program calls break. A program will often need to evaluate a condition with a loop. A condition will wait a second. A condition loops with while. A program will often need to evaluate a condition within a loop. While the condition is true, the loop runs. When the condition ceases to be true, the program calls break. Stopping the loop, it's possible to implement the behavior like this using a combination of loop, if else, and break. You could try that now in a program. If you'd like, however, this pattern is so common that Rust has a built-in language constructor for it, called the while loop. In listing 3-3, we use a while to loop the program 3 times, counting down each time, and then after the loop, print a message and exit. However, this pattern is so common that Rust has a built-in language constructor for it, called the while loop. In listing 3-3, we use a while to loop the program that 3 times, counting down each time, and then after the loop, print a message and exit. However, this pattern is so common. That Rust has a built-in language constructor for it. If you like, however, this pattern is so common that Rust has a built-in language constructor for it. Call a while loop in listing 2-3. We use a while to loop the program 3 times, counting down each time, and then after the loop, print a message and exit. Counting down each time, and then after the loop, print a message and exit. Counting down each time. Here, it's counting down each time. Counting down each, okay. And then after the loop, we print a message and exit. Listing 3-3, using a while loop to run code while a condition holds true. Listing 3-3, using a while loop to run code while a condition holds true. Using a while loop to run code while a condition holds true. Using a while loop to run code while a condition holds true. This construct eliminates a lot of nesting that would be necessary if you use the loop if else and break, and it's clearer. While a condition holds true, the code runs. Otherwise, it exits the loop. Looping through a collection with for. You can choose to use the while construct to loop over the elements of a collection, such as an array. For example, the loop in the listing 3-4 prints each element in the array A. You can choose to use the while construct to loop over the elements of a collection, such as an array. For example, the loop in listing 3-4 prints each element in the array A. Oh my god. Okay. Looping through each element. Looping through. Looping through each element of a collection of using a while loop. Looping through each element of a collection using a while loop. Looping through each element of a collection using a while loop. Here the code counts up through the elements in the array. Here the code counts up through the elements in the array. Here the code counts up through the elements in the array. Here the code counts up. Here the code counts up through the elements in the array. Here the code counts up through the elements in the array. Here the code counts up through the elements in the array. Mute index 0, A index. Yes. It starts index 0 and then loops until it reaches the final index in the array. And then loops until it reaches the final index, and then loops until it reaches the final index in the array. And then loops here, loops until, and then loops until it reaches, and then loops until it reaches the final index in the array. Yes, that is when index is no longer true. Running this code will print every element in the array. Running this code will print every element in the array. Running this code will print. Running this code will print every element in the array. Running this code will print every element in the array. Running this code will print every element in the array. Yes, that's true. All 5 array values appear in the terminal as expected, even though index will reach a value of 5 at some point. The loop stops executing before trying to fetch a 6's value from the array. All five array values appear in the terminal as expected, even though index will reach a value of 5 at some point. The loop stops executing before trying to fetch a 6's value from the array. 1, 2, 3, 4, 5. Value from the array. However, this 1, 2, 3, 4, 5, what? 0, 1, 2, 3, 4. However, this approach is very error prone. We could what? We could cause the program to panic if the index value or desk condition are incorrect. For example, if you change the definition of the array to have 4 elements but forgot to update the condition to while index is greater less than 4, the code would panic. 3 elements but forgot to update the condition to right. The code would panic. It's also slow because the compiler adds runtime code to perform the conditional check of whether the index is within the bounds of the array on every iteration through the loop. Array type 4 elements is also slow because the compiler adds runtime code to perform the conditional check of whether the index is within the bounds of the array on every iteration through the loop. As a more concise alternative, you can use a for loop and execute some code for each time in a collection. A for loop looks like the code in listing 3-5. For loop here like this, okay. Looping through each element of a collection using a for loop. When we run this code, we will see the same output as in listing 3-4. More importantly, we've now increased the safety of the code and eliminated the chance of bugs that might result from going beyond the end of the array or not going far enough and missing some items. When we run this code, we will see the same output as in listing 3-4. When we run this code, we will see the same output. When we run this code, we will see the same output as in listing 3-4. When we run this code, we will see the same output as in listing 3-4. More importantly, we've now increased the safety of the code and eliminated the chance of bugs that might result from going beyond the end of the array or not going far enough and missing some items. When we run this code, we will see the same output as in listing 3-4. More importantly, we've now increased the safety of the code and eliminated the chance of bugs that might result from going beyond. When we run this code, we will see the same output as in listing 3-4. When we run this code, we will see the same output as in listing 3-4. So we will see the same output as in listing 4. Okay, we now increased the safety of the code and eliminated the chance of bugs that might result from going beyond the end of the array or not going far enough and missing some items. Using the for loop, you don't need to remember to change any other code if you change the number of values in the array, as you do with the method used in listing 3-4. The safety and conciseness of for loops make them the most commonly used for loop constructor in Rust. Even in situations in which you want to run some code a certain number of times, as in the countdown example that used a while loop in listing 3-3, most stations would use a for loop. The way to do that would be to use a range provided by the standard library, which generates all numbers in sequence starting from one number and ending before one other number. Here's what the countdown would look like using a for loop. And another method we've not yet talked about. REF to reverse the range. Oh my god. The safety and conciseness of all loops make them the most commonly used loop constructed in Rust. The safety and conciseness of all loops makes them most commonly used loop constructed in Rust. Okay. Even in situations in which you want to run some code a certain number of times, as in the countdown example that uses a while loop in listing 3, most of the time you do use a for loop. The way to do that would be to use a range. Provided by the standard library, which generates all numbers in sequence, starting from one number and ending for one other number. Here's what the countdown would look like using a for loop and another method we have not yet talked about, REF. Reverse the range. Reverse range here. 4, 3, 2, 1. Lift off. True, false, the code will terminate and not loop to crash. This code will terminate and not loop or crash. Exists less than 1, so what here? Is break B, break B, this B, so break it and then goes here. Add x plus 1, 2, 3, 4, 5, 6, 9, 10. So when it's 10, then go to 11, continue away. Continue away. Of course. Determine whether the program will pass the compiler. I think I will determine whether the program will pass the compiler. Passes 5. 5, 10. So meaning the 10 and then value 5. 10, 10, 10, 10, 10. Okay, so actually, so 5 plus 5 is 5, 5. So 5, 5, 10, 15, 20, 25. Value 50. No, recommend. 50, yep. Does it compile? And then 50. Fuck. Yes, this is true. Because this will go to terminate because look at this 11. 11, then it's 11, continue away. This code will terminate and not loop or crash. Continue A. Oh, so here it's like this here. So mean that B here 11, 11, 11, 11, 11, 11. Break. 11, 11. Okay, we're just going to 1. Then there's break B. Just breaks. Then it goes here, break. And then break. And then terminate. Yes. To compare 15. Summary finally. Oh, you made it. That was a sizable chapter. You learned about variables, scalar and compound data types, functions, commands, if expressions, and loops. To practice with the concepts discussed in this chapter, try building programs to do the following. Convert temperatures between Fahrenheit and Celsius. To practice with the concept discussed in this chapter, generate the nth Fibonacci number. Print the lyrics to the Christmas Carol. The 12 days of Christmas, taking advantage of the repetition in the song. When you are ready to move on, we will talk about a concept in Rust that doesn't commonly exist in other programming languages: ownership. When you are ready to move on, we will talk about a concept in Rust that doesn't commonly exist in other programming languages: ownership. When you are ready to move on, we will talk about a concept in Rust that doesn't commonly exist in other programming languages: ownership. When you are ready to move on, we will talk about a concept in Rust that doesn't commonly exist in other programming languages: ownership. When you are ready to move on, we will talk about a concept in Rust that doesn't commonly exist in other programming languages: ownership. When you are ready to move on, we will talk about a concept. When you are ready to move on, we will talk about a concept. Print the lyrics of the Christmas Carol, though 12 minutes of taking advantage of the repetition of the song. Play the lyrics of the Christmas Carol, the 12 days.